Nothing escapes a black hole. That is what every textbook tells you, every documentary, every scientist for the last 100 years. But there is a problem. The laws of physics, the same laws that built your phone, your plane, your entire world, say that something must escape. That information cannot simply vanish, that the universe does not forget. Black holes say otherwise. For 50 years, this contradiction has been the most dangerous unsolved problem in all of physics. It pitted Einstein against Hawking. It broke equations that survived every test we ever threw at them. And in the last 3 years, scientists found something. Not an answer. Something stranger. A crack in the paradox. This is the story of what happens when you fall into a black hole, and why physics is not sure it has ever told you the truth. To understand the paradox, you need to understand the trap. A black hole is not a hole. It is not empty space, not a void, not a tunnel through the cosmos. It is an object, the most extreme object the universe knows how to make. When a star dies, a star many times larger than our sun, gravity wins. Everything collapses. The core compresses into a point of infinite density, a singularity. Around it forms the event horizon, not a surface, not a wall, a boundary, invisible, unmarked, irreversible. Cross it, and the universe ends for you, not because something kills you, because the geometry of space-time itself only points one direction, inward. Time, space, matter, light, everything beyond that line bends toward the center. There is no up, no out, only the singularity waiting. And yet the event horizon looks like nothing. If you could hover at its edge, you would see space, stars, the distant glow of your home galaxy. Then one step forward, and everything you ever were begins moving toward a point no larger than a particle. Here is where things get interesting. You think falling into a black hole means instant death. It does not. At least, not immediately. For a supermassive black hole, one with billions of solar masses, the tidal forces at the event horizon are survivable. Gravity pulls your feet harder than your head. But for something that massive, the difference is still within human limits. You would fall. In silence. No fire. No explosion. Just the steady, irreversible pull of gravity you cannot fight. But here is what no textbook can fully show you. Time stops working. Not metaphorically, literally. The closer you fall to extreme gravity, the slower time runs for you relative to everything outside. An observer watching from a safe distance would see you slow down, then freeze, then fade, redshifted by gravity until your image stretches across the event horizon like a ghost. They would never see you cross it. To you, the crossing is instant, unremarkable. And then, at some point past the horizon, the tidal forces become unimaginable. Your body stretches. Atoms separate. Matter becomes a stream of particles falling toward the singularity. Spaghettification. The physics term for total molecular destruction. But here is the question that broke physics. What happened to the information, the exact quantum state of every particle that made you, when it fell in? Because according to quantum mechanics, that information cannot simply stop existing. This is the problem. Quantum mechanics, the theory governing everything at the atomic scale, has one absolute rule. Information is conserved. Not matter. Not energy. Information. The precise description of the state of every particle in the universe. It can change form. It can scatter. It can become impossibly complex, but it cannot disappear. It is permanent. And then Stephen Hawking looked at black holes in 1974 and found something that should not be possible. Black holes evaporate. Over trillions of years, quantum fluctuations at the event horizon cause the black hole to slowly release energy. This is called Hawking radiation, and it carries no information about what fell in. It is thermal, random, a ghost of a signal with no memory. which means when the black hole finally evaporates completely, permanently, everything that fell in is gone. The information of every particle, every person, every star the black hole ever consumed, erased. But that is impossible. Quantum mechanics says so. And general relativity, Einstein's framework, says black holes do exactly what Hawking calculated. Two theories, both proven, both correct, both contradicting each other completely. This is the black hole information paradox. And for 50 years, the smartest physicists alive could not solve it. Hawking spent the rest of his life circling this problem. In 2004, he changed his position. He bet, literally with a public wager, that information was actually preserved, that it leaked back out through Hawking radiation in a form so complex it was practically impossible to decode. But technically, it was there. He conceded the bet. He paid it. And he died without knowing if he was right. In 2012, a group of physicists found what they called the firewall paradox. They ran the mathematics of information escaping through Hawking radiation to its logical conclusion. And if information does escape, if it is encoded in the radiation leaving the black hole, then the surface of the event horizon cannot be smooth, silent space. It must be a wall of fire, a quantum firewall of infinite energy burning every particle that crosses the horizon. Instantly, completely. No peaceful fall, no quiet crossing, no time to think. Just fire. But the firewall violates Einstein's equivalence principle, the bedrock of general relativity, which says free-falling through gravity should feel identical to floating in empty space. You should not feel the horizon. So now there are three options. Only three. Quantum mechanics is wrong. General relativity is wrong. Or there is something else, something no existing theory can yet describe. In 2019, something shifted. Physicists from MIT, Stanford, and the Institute for Advanced Study published calculations using a framework called the island formula. It is built on the holographic principle, the idea that the information content of a three-dimensional region of space can be fully described on a two-dimensional boundary. Think of it this way. Everything inside a black hole might be encoded on its surface, like a hologram. The event horizon as a screen, carrying the information of everything that ever fell in. Not destroyed, not erased, compressed. The island formula produced, for the first time, a mathematical curve called the Page curve. Don Page, a former student of Hawking, predicted in 1993 that if information is truly preserved, the entropy of Hawking radiation should follow a specific pattern. Rise, then fall. For decades, no one could prove it. The island formula produced exactly that curve. Not proof, not a complete solution, but the first mathematical result consistent with information being preserved. A direction, finally, that does not contradict everything we know. We do not yet know what the holographic encoding looks like from inside the black hole. Whether the firewall exists, whether anything feels the crossing, we do not yet know. And that might be the most honest thing physics has said about black holes in 50 years. So, what happens when you fall into a black hole? Physics says you are torn apart, turned into a stream of information falling toward a singularity. Physics also says that information is preserved. Somewhere, somehow, encoded on the event horizon, leaking back into the universe through radiation so complex it would take longer than the age of the universe to decode. You would become, in a strange sense, eternal. Not you, not your body, not your memory or your name, but the precise quantum description of every particle that made you would not cease to exist. It would just become unreadable. And the universe, indifferent, mathematical, governed by laws that do not care about the difference between a person and a photon, would carry that information forward. Forever. Not filtered through philosophy, not reconstructed from belief. Written in mathematics. Black holes do not destroy. They remember. We just do not yet know how to ask them what they know. Subscribe to Astronus. Because beyond the paradox, there is still something left to discover. Join us as we explore the unknown together.